All right, we're going to do example number 11, where we're going to show how we can use function notation to write something that we may do in our, we'll call it everyday world, but usually appears most often in our science world. But example number 11 here says the perimeter of a rectangle is P is equal to 2L plus 2W. If it's known that the length must be 10 feet, then the perimeter is a function of the width. So I'm going to say the perimeter, P, right, is a function of W. And so that is 2 times the length, and if the length is 10, I'm going to substitute that in, and then plus 2 times the width. And therefore you see the only variable left in this is W. So we simplify 2 times 10, which makes 20, and that's 20 plus 2W. And that's the perimeter as a function of the width. And you see how the P relates to the perimeter and the W relates to the unknown variable. And so I just succeeded in writing this as function notation, which is part A. And you see how those two parts relate to the function notation and the independent and dependent values. And then it says find the perimeter given the width is 2 feet, and write this using function notation. Well, we're being asked to say that P of 2 is equal to what? What's the perimeter when the length is equal to, or the width is equal to 2 feet? So this is 20 plus 2 times the width, which is 2 feet. And what's that equal to? Well, that's 20 plus 4, which is, of course, 24. And that's feet, so we'll write that out, 24 and feet. So when we write that P of 2 is equal to 24, we see that the perimeter, when the width is equal to 2 feet, is equal to 24 feet. And that's a very, very nice relationship, and it succinctly tells us what it is we're talking about and what two things are being related. And that's why we like function notation, as well as the fact that it very easily gives us a way of saying, let this be this, and then find out what that equals without all those silly words. All right, our next task is to find output values when we have input values. So first of all, that we understand that the x value is within the parentheses, and when we say f of x, we're asking for the y. And we're going to input x values to the model and solve for the dependent, the y value, the f of x value. And if we find the x value in the table, and then we can look at its corresponding dependent value, or we can find the x value on the graph, follow a vertical line up, and find then where it goes to on the dependent axis. So we're going to do these 3 examples here in example number 12 and show how we can do this in each case. So in part A we have a function, so we want to find f of 5. We're doing exactly the same thing as we were in the last examples. F of 5 is 2 times 5 plus 3. And so we have 2 times 5, which is 10, plus 3, which is 13. And so that was very easy to find what we had been doing previously. Now if we want to do it with a table, we find the x value, 5, and then we follow it down to the y value. And so here we see that f of 5 is equal to, and the y value here, the f of x value is 15. And so that's what we write. And then finally here, we're going to go across and we see the x's, the independents here, right, are by 2s. So 5 is right here. We'll follow it up to the graph and then back across to the y's. We did this back in chapter 2. And now we see that f of 5 from this part is equal to positive 2. And that's how we'll find the output values based upon the independence. And we can do this for graphs and tables and functions. In our next little video, we're going to be doing the opposite of this. We're going to find input values when we have the output values. And so I'll see you in the next video to conclude that one.